Hello, welcome everyone. In this video, my classmate Julia Monar, Marina Suarez, and myself, Elena Salvat, are gonna present exercise 5.6 from chapter 5, magnetostatics. First, we're gonna see a little introduction. Second, we're gonna see each statement and we're gonna talk about some previous considerations on how to approach the problem. Then we're gonna go through the resolution of the force and the torque, and finally, we're gonna talk about some conclusions we extracted from this problem. Okay, so first of all, before starting with the resolution of this problem, we want to emphasize some things that will be important for this exercise. Regarding electromagnetic loops, we will say that if the electromagnetic field B is constant through the loop, the force exerted by B by the electromagnetic field on this loop will always be zero. Just remember that a loop is a plain closed wire, and as I've just said, we will use problem 5.6 to demonstrate this statement.
We have the statement of our exercise. A wire forms a right triangle of short sides A and B and hypotenuse C. The triangle is placed in an homogeneous magnetic field parallel to A, as shown in the figure. Calculate the force and the torque when a current I flows through the wire.
So now we will make some previous considerations on how to approach this problem. In order to simplify its resolution, we will divide the wire in three segments, A, B, and C, which are the sides of the triangle we've just seen in the last slide. To obtain the total force when a current I flows through the wire, which is what the problem is asking us, we will follow the same procedure for each of the three segments, and the final result will be the sum of them all, of each one of the forces of each segment.
Before calculating the force for each wire, we're going to explain a little bit about the theory behind it. First of all, we have to know that our differential of force of a magnetic force is calculated multiplying the intensity by the cross product of our differential of L and the field. From here, what we're going to do for each segment is to calculate the modulus, doing the cross product, and we'll obtain the formula intensity multiplied by the dl multiplied by the field and the sign of these two vectors. And to know the vector's orientation, we will follow the right-hand rule. Plus, we found it interesting to know that the formula of the magnetic force on a wire is given by the formula of the Lorentz force, knowing that our differential of Q is the charge density multiplied by our differential of volume. And substituting these two expressions, we'll obtain the formula of the magnetic force on a wire.
On segment A, we get that the differential force will be intensity times dl times the electromagnetic field sine of theta. Theta will be zero because the electromagnetic field is parallel to the segment, so the total force on A will be 0 newtons.
Now we are going to calculate the force exerted by segment B. The first thing we do is to write the force differential equation for a wire. We see that in our case the angle is B halves. Then we integrate, and since I and B are constant, we can take them out of the integral. After we've done the integration process, we obtain that the force in B equals intensity by the magnetic field by B newtons. By applying the right-hand rule, we see that our vector points upwards.
What we do for wire C is to decompose it into the two different axes. We start by calculating the differential of force of X, which is the multiplication of the intensity by the dl of X by the field and by the sine of the angle. As we said before, this angle is pi, and as the sine of pi is 0, the force of X equals 0. To calculate the differential of force for the y-axis, we multiply the intensity by the dly by the field and by the sine of the angle, knowing that this angle is p halves. Plus, to know the differential Ly, we multiply the differential of L by the sine of alpha. And as we're working on a triangle, alpha equals V divided by C, which is the opposite catet divided by the hypotenuse. Then we integrate the differential of force y from 0 to c, and we obtain the result intensity multiplied by field multiplied by v. Moreover, with the right-hand rule, we calculated the direction and obtained that it points inwards. As we explained before, to calculate the total force, what we have to do is to sum all the forces. On this problem, we have two forces, which have the same modulus and are in opposite directions, so the resultant force is going to be 0. With this, we have demonstrated that the total force on a loop is always 0.
Before doing the resolution, let's make a brief theoretical explanation of the torque. The torque on a loop in a uniform magnetic field B and with a magnetic dipole moment M can be calculated by doing the cross product between vector M and vector B. Provided that M equals I times S, the torque's modulus is the product between I, S, B and the sinus of the angle between vector S and vector B. We know that vector M is parallel to vector S. We follow the right-hand rule to calculate the orientation of the torque's vector.
Okay, so we know that the torque's modulus is intensity times the area of the triangle times the electromagnetic field and sine of theta. The area will be AB halves and theta will be P halves as the magnetic dipole moment and electromagnetic field are perpendicular. So we get that the torque will be intensity times the area times the electromagnetic field, newtons per meter.
And to conclude, this exercise proves that the force on a loop is 0 if the magnetic field is constant through the loop. Even though some forces will be exerted on different segments, this will always counteract each other. Hence, the total sum always equals 0. Nevertheless, this doesn't imply that the torque has to be 0, as we have just proved. To verify the results obtained, we have used the units to demonstrate that it is dimensionally correct.